there. Today we're going to look at these graphs. Yesterday we did the polynomial functions and all the bouncing and the cutting. And so today we're going to look at looking at a rational function and trying to graph that. So you should have a new packet in front of you. We're using that, not really a notes packet, but this will be your notes and your homework packet. All right, let's jump in and look at yesterday's just to clean that up. A few things that are some common mistakes that I see on this that I want to draw your attention to about the polynomial function. All right, so on this particular example, and you can go find it in your polynomial packet, but did you notice this lone x sitting out here? This is ultimately just an x minus 0, like another quantity there. So it does affect the end behavior. When you're counting up how many x's do you see, that counts as 1. And then there's 2 for this one because it's squared. There's 5, there's 3, and then there's 1 more. And so what do we end up with there? That's 8, 9, 10, 11, 12. So this should have been an x equals, up here, an x to the 12th power. So that's an even, which means you should be starting high and ending up high. It also creates an extra x-intercept, yes, but it also ends up being your y-intercept also because it crosses at the origin. The other thing I want you to do is look back at any of the problems because classic mistake, I do it, it's like you don't even notice there was a negative on the front until after you're done graphing the whole thing. But so go back and look at all of those, check that leading coefficient out there. Is there a negative? Did you remember to flip your graph? Okie doke. And then the other thing, sometimes we just get in our groove and we start graphing and we don't fill in all of this information over here. That is part of what I'm grading you on. So go back and make sure you've actually filled in all of the boxes. One thing, again, common mistake is when it says in behavior, you just are counting up the x's, and so then you just say, oh, it's a y equals 8 because there's 8 x's. Nope, that's a horizontal line at 8. That's not what your in behavior will look like. Your in behavior would look like this, an x to the 8th. These are not the same thing, so check that also. So let's move on to rational functions. Now, what makes it a rational function is that it's written like a ratio, so as a fraction. So all of our functions today are going to be fractions of some sort. Now, before we jump in, there's some new notation that we need to talk about, and it's a part of our arrow notation. As x approaches some number, what is your y approaching? So we have a new symbol here. As x approaches some number, and then we have this little plus sign at the end. What that means is you are only approaching that value from the right. If you put a little negative, then you are approaching that value from the left side. Now notice this is not like a negative, it's not in front of it, it's not making your a negative. This just means you're going to approach from the left. And then we've already kind of talked about this as x approaches infinity or as x approaches negative infinity. All right, this is kind of a standard graph. It's just your parent graph, almost a parent graph of a rational function. Regardless, I just want to look at the end behavior on this. So looking at this first one, it says, as x approaches 1 from the right. So your x values, you're looking at your x-axis. Here is 1 on the x-axis, and you are going to approach from the right side. So you come way over here on the right, and you jump on the graph, and you start following it. Now, what is your y value approaching as you get closer and closer to that 1? All right, you should be saying, oh, well, that approaches negative infinity. All right, how about if we approach 1 from the left side? So then we came way out to the left, jump on the function, and start getting close to x equaling 1. In this case, it's going up, 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 so the y value is approaching a positive infinity. And then here's a new one. What if x is approaching infinity? Be careful here. As x starts heading out towards infinity, what is my y value getting really, really, really close to? All right, there's an asymptote going on right here, and that is never going to cross over. So my y value actually is approaching 1. So it's not always going to be an infinity and negative infinity, sometimes it approaches a value, a whole number. Okay, so let's start looking at what graphs, rational graphs look like. This is the standard. It's just a 1 over some sort of a polynomial function. And it starts off as basic as we can make it be. It's just a 1 over x. Now, this is a graph you would have seen before. In class, we did a lot of playing around on our graphing calculator, looking at these graphs, seeing what happens. I'm going to cut to the chase because you're watching the video and you've probably got plenty of makeup work maybe that you're working on, so we're going to hurry this along. So when we plugged in a 1 over x in our calculator, here's what it looks like. It has starts over here on the left, and it comes down, and then it comes up here and does the same thing up in the first quadrant. Now, we have two asymptotes here. You have an asymptote going on right here that it'll never cross, and you have one here that it never crosses. Now, as we started to up the power in that denominator, in that x value, so you can see each time I'm adding in another x value. Now, the graph started to change, obviously. What happens, and this might just make common sense, that if you have your x, and now all of a sudden that x is squared, it doesn't matter what your x value is, you're going to end up with a positive, because when you square it, it's going to make it positive. So ultimately, that bottom piece of the graph pops up, and it goes this way. It's up in the second quadrant instead of down in the third quadrant. And the other one just stays the same. Okay, if you go back to a cubed, now you're back to being able to let that be negative. So now we're back down here. Now, of course, the graph changes more than that. We start to notice that this has kind of a sharper turn as it graphs. But really what we're looking for more here is the location of this. I'm back to a 4th degree, so these have to both be positive. I'm at a 5, so now I could have a negative. Okay, what's the big difference here? What do you notice happening? When is it able to be negative and when is it not able to be negative? Hopefully you're saying, well, obviously evens. Even powers would pop that up and make everything positive. If you have odd powers, then you could have it still down in that third quadrant. So that's the next thing we need to talk about then. Consider the odd and the even functions. Notice what happens at x equals 0. Okay, so really, it's not just what quadrants it's in, but what happens as your x gets closer and closer to 0. So we already discussed that the odds will look like this, whereas the evens will look like this. You don't need to draw this. You have it right there on the previous page. Ooh, that's kind of messy. Sorry. Okay. So this is kind of the gist of it. Those are the two graphs. So what happens as your x on this odd, let's start here, as your x gets closer and closer to 0. And then at 0, it flips up here and it's way up above the x-axis. And then it takes off into this new branch. We call those branches of your graph. Whereas on the even powers, when they're both up, this kind of goes up, 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 up. And then when it jumps over that x equals 0, because it can't be 0, there's an asymptote there because you can't have a 0 in your denominator. So you don't allow x to be 0. But as you get close to that 0, and then you create that second branch, it stays up there where it's at. We say that it is either a flip or a no flip. So on the odds, as this is coming down, 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 it flips and it's way high. So when you're flipping from one side of the x-axis to the other, the x-axis, that's a flip. So it's going to flip on the odd powers, but here on the even powers, wherever it's at, it stays. All right, so with that, do you think that you could describe this graph? What's different here? Well, it's an x plus 3 instead of an x minus 2. So that means x cannot be negative 3. So instead of my graph moving to the right 2 and putting a vertical asymptote at 2, my graph is going to move left 3, and I'm going to have a vertical asymptote at negative 3. And as far as the whole flip, no flip thing, well, it's basically going to have this asymptote right here. And because this quantity is to the first power, that's going to make it be a flip because 1 is an odd. So I would draw it like this, and then it would flip way up high, and it would go like this. All right, now, as I did that, I realized, I never really talked about that whole end behavior thing. Like, what is, okay, yes, I can say that the end behavior looks like a 1 over x or a 1 over x squared. Here's what I mean by that end behavior. Here's a 1 over x. Here's a 1 over x squared. As far as end behavior, well, if I have an odd, x to the first, x to the third, x to the fifth, whatever, I'm going to start below the x-axis because I'm going to have this piece, this negative piece that's down below. So you're going to start underneath the x-axis. It's going to go do this. This example flips. And then end behavior-wise, I am landing, or I am starting here right underneath the x-axis, and I am ending above the x-axis. Whereas if I have an x to an even power and they're both up, then I start my graph above the x-axis here, do all the stuff, and end above the x-axis. So that's what we're talking about when we do this end behavior. Which one of those scenarios do we have? Ultimately, you can see they end the same. They should be ending above. But do you start below the axis or do you start above the axis? Well, on this example right here that I'm going to do, I have an x minus 2 and an x minus 4. All right, so now I have 2 restrictions. X cannot be 2, x cannot be 4. That's going to create 2 vertical asymptotes. And so you can see here I've written that I'd have asymptotes at their vertical asymptotes. So I write x equals 2, 4. So I've got 2 of them, at 2 and at 4. So I'll go ahead and put those in. But overall, if you just look at what this would be, this is ultimately a 1 over x squared because I have an x here and another x, so that's going to get me a 1 over x squared. So my end behavior is going to do this right here. This is the even situation. I'm going to start above the x-axis and do all the stuff and then end above the x-axis. Individually, these are each to the first power. So they're going to end up being flips at each of those asymptotes. So let's just jump in and graph this baby. All right, so it's going to start above the x-axis because it behaves like a y equals x squared, comes up here and goes up. Now, I don't have any x-intercepts on these graphs. Can never touch the x-axis. And at this asymptote, because x minus 2 is to the first power, and that's odd, and odds are flips, as I come up, 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 I'm going to flip, and I'm going to start way down low. I'm going to come up, can't cross the x-axis, so I turn that baby around and go down, down, down. All right, I come across this asymptote, which is also to the first power, which means it's an odd, which means I'm going to flip. So since I ended way low, I'm going to start way high. And then I'm going to level that thing out. And it looks like the end behavior I just drew right there. All right, now the last thing here I have is just a little bit of practice with the arrow notation. As x approaches 2 from the left. All right, so here's my 2. There's an asymptote going on. But I'm going to approach that asymptote from the left side. So I'm coming in this way, coming in. As x approaches 2 from the left, what is my y value approaching? It's approaching infinity. And that's a different answer than if I would have put a little plus sign and said I'm going to approach 2 from the right. If I was approaching 2 from the right, I'd grab onto this function here, getting closer and closer to 2. My y value is actually approaching negative infinity. All right, let's try something more fun. Here we go. Let's look at how many x's you've got in the denominator on this example. You have an x squared. So that's 2. That counts as 2. Here's another one. There's 3. There's 4. There's 5. This behaves like a 1 over x to the 5th, which means for end behavior, Since 5 is an odd, it's going to look like this. So again, when I draw that, I'm really only looking at where do I start, where do I finish. Because I have so many restrictions in my denominator, so I can see right here, x cannot be 0. It cannot be 3. It cannot be 4. It cannot be 7. I have 4 different vertical asymptotes in here. So let's put those in. I've got a vertical asymptote at 0 and at 3 and 4 and at 7. Now, do they flip or not flip at each one of those asymptotes? Well, it depends on their individual powers. And so this 0 is squared. That's an even power. Oh, look at this. I have a typo here. I didn't go change this. It's not a bounce. We're not talking bounces and cuts. It's flips and no flips. Let's correct that right there. I will script. Maybe it's fixed in yours by now. I don't know if I've done that or not. It's a no flip, not a bounce. Okay, doke. So it's an even power, so it's a no flip. But the other 3 all are to the first power, so those are all going to be flips. I'm going to start here and just start approaching those asymptotes and doing my thing. So I'm starting right here, coming in. It's going to go down, approach this asymptote. Got it. Now that's 0. And we said at 0, it's a no flip. So since I ended way low, I'm going to stay way low. And then I come up here, and I can't cross the x-axis on any of these, so I'm just turning them around. All right, now this asymptote is a 3. It's a flip. So since I ended low, I've got to start the next piece way up high. Turn that thing around. It's another flip, so now I'm going to come down here. Do this again. It's another flip, so I'm going to come way up high. And now I'm kind of done. No more stuff, so I finish that off like my end behavior tells me to do. I'm going to level off right here, like we did right there. So let's do some arrow notation. As x approaches infinity, x is going out as far as it can to infinity. What is our y value approaching? 0. All right, so I'd like to see if you could try one of these on your own before we keep moving along. So this one is for you. If you could pause the video and try this one on your own, that would be awesome. Don't let me do all the work. You got to try something on your own without me guiding you to see. And so I want you to pause the video. When you've done what you think is correct, then come back. All right, if this is what your graph looks like, give yourself a smiley face. If it doesn't, then take a minute and compare mine to yours to see where you might have gone wrong. All right, last thing I didn't fill in the box. As x approaches 2 from the right. All right, so here's 2. I'm going to be on this little shape right here, and it's approaching. It's getting closer and closer to 2. Looks like my y value is headed downward, so I'm going to say negative infinity for that piece right there. Yay. Okay. All right, so this up here is just for me pacing us in class. So as soon as we did this in groups, and so soon as somebody got to this stage right here to part C, we went ahead and moved on. If it were me, I would pause the video and go work on your sheet until you get to part C, and then come back to me. So you want to practice that skill, what the whole flipping, no flipping, before you jump into this part. All right, so let's do it then. Notice my function this time. I have things in the numerator other than 1 now. Now, that actually goes back to our polynomial function. Anything up here that will turn this into a 0, anything that makes the numerator 0, it's going to create a 0. And so then I'm going to be looking at bounces and cuts from anything in the numerator. But now I also have things in the denominator, and those are going to create those vertical asymptotes. And that's where I'm going to be paying attention to the flips and no flips. So there's a lot of pre-work to go into this before you jump in and start graphing. So let's do some of that. Of course, it looks like I've got it all done, but let's talk through this. You have to count up how many x's you have in the numerator. So there's 2, 3, 4, 5. So I have an x to the 5th on the top. And then I have an x squared on the bottom. So we write it like this, but we just use our exponent rules. That would reduce to x cubed. So my end behavior is actually an x cubed. An x cubed means I'm going to start low. It's going to have some bouncing, cutting, flipping, no flipping, all the stuff, and it's going to end high. Next thing, anything in the numerator creates zeros. So I'm going to have a 0 at 0, -3, 4, and -9. I've already marked them, and I've marked them as bounces or cuts based on their individual powers. Then I put in my asymptotes at 5 and -6. These are both to the first power, so they are both flips. You can see I have a little F there for flip. All right, one other thing that we're going to work on is start looking at a y-intercept. That helps us to keep our graph accurate. Now, there is no y scale, and that is intentional, and so I don't know necessarily that I'm going to be able to plot it exactly, but by finding the y-intercept, it is a good check if I'm on the right track on my graph. So in this case, it actually is a very easy one, because to find your y-intercept, you plug 0 in for x. So I put a 0 here and get 0. Put a 0 here and I get 3. Put a 0 here and I get -4. You can see what I'm doing here. Put in a 0, get a 9. And then in the denominator, I get a -5 and a 6. And then I can just type this in my calculator to figure it out. However, I got lucky because there's a 0 here. So that's just all going to end up equaling 0, and 0 over anything is 0. And so the y-intercept is 0. Now, actually, that should make sense because I had a bounce going on at 0. And yeah, that's where it's touching the y-axis also. All right, got it. Now, I love doing these. I think they're kind of fun. You're just going to move left to right, and you're going to start like they want to, and you're going to hope it ends like you want to. So I'm going to start way low. And I just start reading that graph left to right. The first thing I do is I come across a cut. So I'm going to kind of swoop in, cut through there. The next thing is an asymptote, so let's go approach that. And then I have to look at that. Do I want to flip or not flip? I want to flip. So that means since I ended going way high, I'm going to start way low. Down here, next thing I get is a cut. So I come up and cut. Oh, then there's a bounce. So I'm going to bounce. There's another cut. Okay, and again, remember bounces are curvy bounces, not pointy. And then I'm going to cut and go down, 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 down. All right. This asymptote is another flip. So I'm going to flip here, and I'm out of stuff. So now I have to depend on my end behavior over here. This is supposed to end going up, and I don't feel like I'm going up. So what you do is you just turn her around and head up. And that's my graph right there. All right, let's try another one of these together. I'm going to start off, and I'm going to look at what is my end behavior. So we count the x's. There's an x and an x, so there's an x squared on top. X times x times x times x, that's an x to the 4th. X squared over x to the 4th would reduce to a 1 over x squared. That means that I want my graph to look like a 1 over x squared. Remember from earlier, this is what a 1 over x squared looks like. And specifically for end behavior, that means I want to start here like close to the x-axis, and then I want to end over here close to the x-axis. The numerator gets me my zeros, so I'm going to have a 0 at -1 and 2. These are both to the first power, so they are both cuts. I have that already marked. The denominator is going to give me all of my asymptotes. I'm going to have 4 vertical asymptotes. They're all to the first power, so they are all going to be flips. I already have the little f's there, but I do need to put in my asymptotes. So let's go ahead and draw in our vertical asymptotes. And then before I get started, I want to figure out what my y-intercept is. I'm going to put a 0 here. That's a 1. Put a 0 here. That's a -2. 1 times -2 is -2. And the denominator, I'm going to end up with a -4 times a -6 times a -8 times a +2, all multiplies to a -386. Negative over negative is going to end up a +1 over 193. Okay, that's a pretty tiny value. But one of the things I'm really looking at is it positive or negative? And it is positive. So in my mind, what I like to do is I like to go ahead and put a little dot on my y-axis. I am going to be above, somewhere on this y-axis above, because it's a positive. And it's kind of a nice little check. So as I get to that point, am I in the right spot before I just keep plugging along? I think I'm ready. Here I go. Starting with my end behavior, it's supposed to start like this. Come across an asymptote, go approach it. That asymptote is a flip, so since I ended low, ended high, I'm going to start low. It's going to come up here. Next thing I come across is a cut. So I'm going to cut. Oh, looky, I'm going to go through that little y-intercept I had. Next thing I have is a cut. And then I guess this asymptote. So let's go approach that asymptote. Don't know what that little jerky move was in there, but that's all right. All right, now it's another flip. So I'm going to flip and go way up high. Can't touch the x-axis in here anywhere, so I've got to turn it around. It's another flip. So since I ended high, I start low, come up. I don't see any x-intercepts in there, so I got to turn it around. End low, start high. All right, and then I'm going to level off like my end behavior tells me I'm supposed to. What do you think? Is that doable? It's kind of fun, don't you think? All right, now I have for homework finished through, I don't know, it varies by year how far we get. I suppose if you're watching this, it's maybe because you were absent, so you probably need to get as far as you can because you're probably going to be behind. So get as far as you can, and then once you've done that, let's move on to the next part here. All right, horizontal asymptotes. This is a little bit trickier thing. Let's talk about the end behavior that might happen here. So it says consider this function right here. Let's look at your end behavior. You'd have this 3. That 3 is going to create a vertical stretch. But since I don't have my y-axis scaled, I don't really care about it. It's just there to remind you, hey, there can be numbers. We're just going to ignore them. What I am going to have is, it looks like a 0 at 2, and it's going to be a bounce. But again, I'm looking at end behavior. This is an x squared over an x times x. Oh, so it's an x squared over an x squared. Well, those would just cancel each other out. And all that would be left would be this little 3 guy sitting here. So my end behavior is really just y equals 3. That is a horizontal line. And for my graph, that means I have a horizontal asymptote at 3 that my graph is going to approach. The trick, though, is, all right, so if I have some sort of a graph over here, and I'm going to have this horizontal asymptote, and it's up here instead of being on the x-axis like many times our horizontal asymptote is. But I don't really know, should I be starting below and doing this, or should I be starting above and doing this? I don't know where to start. I also don't know where to end. And so that is what creates an issue for me. The only real way, because there's not a set answer to that question, the only real way to figure it out is to sort of do a test point way out to the end, past all the action of the graph. So I usually would say if I go out to 10 or -10, that's usually out there past where I'm going to be having you draw asymptotes and bounces and cuts and stuff. So what we're going to do, okay, I don't want to get ahead of myself. North side away from 0. Okay, so we're going to plug in a value away from your zeros and asymptotes. So I can see I would have a 0 at 2, I have an asymptote at 5, so 10 is out there ways. So what we're going to do is we're going to plug in 10 for x and see what we get. So that means right here in the function, if I put in a 10 here, that's going to be 8 squared, that's 64 times 3. Put in a 10 here, that's going to be a 9 and a 5, which is multiply gets you a 45. So if I multiply this out, it actually gets me, oh, I hadn't done it yet, but I just have the the fraction written there, but it's good to know what is actually the value. And it is actually 4.2666666. Okay. What I really care about is where does it fall in reference to my horizontal asymptote. I have an horizontal asymptote at 3. And if this is going to get me a 4, then what that tells me is that out there close to the asymptote, I'm going to be at 4. I'm going to be above that horizontal asymptote at 3. Now we're going to do the same thing. We're going to plug in a value on the, oh, sorry, hang on. That was when x was 10. That's out here. Not there. Let me erase that. See if I can. It's temperamental sometimes. Okay. So on the end, I have to be like leveling out and coming up out like this, above that. I've got to do a test point out on the left side also. I've got to plug in -3. Not -3, -10. So here I go. I'm going to plug in -10 into this function right here. I'm going to end up with a 3. -10 minus 2 is -12 squared. That's a 144. Okay, plug in -10 in the denominator. I'm going to have a -11, and I'm going to have a -15. I'm just going to type that in my calculator, 3 times 144. Then I'm going to divide by -11, and I'm going to divide by -15, and I get 2.618. All right. So when I am at -10 for an x value, I'm at 2.6. That would be below that horizontal asymptote. So that tells me I'm going to want this. I am not going to want this scenario right here. All right, it's a little bit tedious. Hopefully you will pick up the speed on it. It won't take very long, but it's the only way to know how to graph these is to put in that test point at 10 and -10, decide how you graph. And again, this is when is it we're doing this? This is when you have the same number of x's on top that you do on the bottom, and they all cancel out, and all you have left it with is y equals a number. That's your horizontal asymptote. If that 3 was not there, we would have assumed it was a 1, and I would have had a horizontal asymptote at y equals 1. And then I would have done a test point at 10 and -10 to see if I'm above 1 or below 1. So now let's graph this thing. I did kind of go ahead and get started on filling out some stuff. I know my end behavior. The x's all cancel out. I get a y equals 3. I'm going to have a 0 at 2 because that is my numerator. The 3 here does not create a 0. It's just at 2. It's going to be a bounce. Let's go ahead and fill that in. It's going to be a bounce because it was squared. All right. My vertical asymptotes are at 1 and 5. Those are vertical, so I wrote x equals. These are both to the first power, so they are both going to be flips. I like to go ahead and write this info in because then when I get to the point of graphing, I just graph and go, and I don't have to keep looking back. Is this a flip or no flip? I just have it all written. I already have the horizontal asymptote in there at y equals 3. Let's look at a y-intercept. Remember, y-intercept, x is equal to 0. If I do that, I'm going to have a 3 times 0 minus 2 is -2, squared is 4. And then I'm going to have a -1 times a -5. So that's 12/5, which is what, 2 2/5? All right, so I feel like then if I've already got my horizontal asymptote, I should be crossing the y-axis at a positive 2 2/5, so somewhere there. And then I went ahead and put just dots on those test points I did at -10. Over here, I was at 2.66. Over here, I was at 4.67. And then, let's see, what else do I have? Okay, I think I'm ready to start. So my end behavior is going to be right here, just approaching that, looking like a horizontal line. Horizontal line at 3, but really close to 3. Now I have to go until the next thing I come across, which is really my y-intercept. So this is really flatlining for quite a while here. And then I can't go down because I don't have any x-intercepts here. So I'm not allowed to take that thing down. I'm going to have to go up. Now that may feel wrong because I am crossing that horizontal asymptote as I do it. That's actually legal. You can cross over horizontal asymptotes like this. We can't cross over vertical asymptotes, but horizontal is okay. The idea behind an asymptote truly is just that it is the value your graph is approaching. And so as long as that's what I'm doing out here, then it's okay for me to cross over it way back in here. Now this asymptote is a flip, so I'm going to come way down here. Next thing I see is a bounce, and then an asymptote, so let's go over there. This asymptote is a flip, so I'm going to come way high, and then I'm going to level off and stay above that horizontal asymptote. Right there. We're going to try one more of these together, then you're going to do a few on your own. Let's go through this from the beginning. Let's start with our end behavior over here, because futuristically, you're not going to know if this is a special horizontal line type of problem or not. I've got 1, 2, 3 x's. This is a coefficient, not a power. So 1, 2, 3 on top, 1, 2, 3 on the bottom. So I've got the same number of x's on the top that I do on the bottom. Here's the problem I have with this particular example that we need to talk through, and it is about this 2 that's sitting here. Now, what do you think this creates for an x-intercept or a 0? It's not 5. If you set this equal to 0, you'd add 5 divided by 2, so it's 5 halves. Well, it's not really just that. This 2 also affects my graph. So instead of thinking about setting each of these equal to 0, what I'm going to do with this is I'm going to factor that 2 out, and it's really going to look like this. And there's my 5 halves. But by thinking through it like that, this 2, which I would actually put on the front of this whole thing, is that coefficient on all of this. So in the last example, I had a coefficient of 3. This 2 is my coefficient on this one. So you can see I've already got my horizontal asymptote drawn in at 2. So there is a horizontal asymptote at y equals 2. Other than that, it's kind of the same deal that we did previously. So my end behavior is going to be a y equals 2. Got the horizontal line drawn. Vertical asymptotes, those are x equals -6, -1, and 7. Let's go ahead and draw those in. Now, those are all to the first power, so these are all going to be flips. And then it doesn't really have a spot for my zeros. I might stick it in here if I wanted to. The zeros are going to be at 2, 5 halves, and 6. Those are all to the first power, so they are all going to be cuts. 5 halves is really a 2.5. Ooh, that's going to be tight. All right, there we go. And 6, got it. All right. Now, because my end behavior is a horizontal line, that's when I've got to do these test points. I'm going to plug in a -10, see what I get back for y. I'm going to plug in a +10, see what I get back for y. I'll go ahead and plug the -10 in this original version rather than this. If I plug in a 10 here, that's going to be an 8. This is going to be a 20 minus 5. That's a 15 and a 4. So 8 times 15 times 4. Plug 10 in the denominator, I get 16 times 11 times 3. So then I just type in my calculator to see what that's going to get me. And I have 0.9. All right, so when I plug in 10, I get a 0.9. That means I am going to be below that asymptote. There's my 0.9-ish. Okie doke. Let's plug in a -10 and see what happens. -10 minus 2, that's a -12. -20 minus 5, that's a -25. -10 minus 16, or minus 6, -16. And then a -10 negative 10, oops, no. Oh, sorry, that's going to be a negative 4 and a negative 9 and negative 17. Okay. And type that in my calculator, see what I get. And I get 7.8. Okay. So that's 7.8. And down here, I said I got a 0.9. All right. So 7.8 is well above. That's way up here somewhere. Okay. So definitely above it. Okay. I think I've got what I need. Now, remember that the end behavior is going to actually be approaching this asymptote. This is sort of hard to maybe envision, but I'm really supposed to be close to my asymptote. But because that is so high, I'm guessing I'm just not very close to the horizontal asymptote yet, but it's going to go like this. And then that asymptote is a flip. So then I'm going to be down here. Don't cross that x-axis. There's no cutting or bouncing going on there. Another flip. So I'm going to be up here. Now I do have some cuts. So remember, it's okay to cross over that horizontal asymptote. I got a quick cut. Oh, I got another cut. And then it's a flip. So I'm up here. And now here, this is kind of weird because it's like this, but remember, I'm not approaching the axis. I'm approaching this horizontal asymptote. So what this graph does, and you can actually see this on your graphing calculator, it'll swoop down and then kind of come back up and go approach your asymptote like that. It gets this little swoop in it and then comes back up where you think it should be approaching. All right, why don't you finish these out? When you get to the back page, then come back to me. Last thing here is the average cost. All right, this is a place where we can use these rational functions, and the graphs kind of help us envision what's going on with this. So I have a situation here. Carly wants to have flowers delivered to a bunch of her friends. She's got to pay $32 up front, but then she can get as many flowers as she wants. So that's kind of a deal, I guess. Maybe. Depends on how many flowers she's wanting to send. But she does have to pay for them to be delivered. So she's going to pay $1.50 for each flower to be delivered. So write a function that represents the average cost of the flower. Now, this is the average cost per flower, not what the total cost is. This is the average cost, depending on how many flowers she sends, obviously. All right, so to figure out what she's going to spend, we are guaranteed she's going to have to pay the $32, but then she's going to pay $1.50 for each flower. So I'm going to do the $1.50 for each flower plus the $32 fee. But that would be her total cost. After you figure out what she's paying, how do you figure out what the average cost per flower was? Well, divide it by how many flowers you got. And right there is the function we're looking for. And these are all kind of set up the same way when you're doing an average cost. You figure out the total cost and then divide by how many you got, which is the x, which is what's creating this rational function here. Now think of it like it looked like this. And then if you were going to graph this like we did earlier, okay, well, you've got 1x up on top, you've got 1 on the bottom, so that's going to end up being a horizontal asymptote situation. And like we did on that earlier problem, I'm going to factor out the 1.5. So it's going to look like 1.5 and then x plus whatever 32 divided by 1.5. I could probably do that in my head, but I'm not. 21.333. Okay. Sketch a graph. All right, will do. Now, the reality here is I am not really all that concerned with anything but the first quadrant because it wouldn't make any sense for me to have a negative number of flowers or to have a negative cost. So ultimately, I am looking only at this first quadrant up here. And then I know that I'm going to have a horizontal asymptote at 1.5. That's at 1.5 there. All right. Now, there's not a whole lot going on here. I am going to have a vertical asymptote at 0. I'm going to have an x-intercept at negative 21 point whatever, which is way out here. And because this is to the first power, it's going to be a flip. I just don't have that much. I don't have numerous quantities here that I've got to deal with. I ultimately have a graph that is going to go like this. It's going to go shoom, and because it's a flip, it's going to go here. So really, this is going to be the only piece I am concerned with. And all of these are going to be like very basic like that. So I'm going to graph this graph right here. It's going to be, that's really what I'm looking at. What is the meaning of the horizontal asymptote? Okay, so this is at 1.5. And in general, what's the meaning? What's going on with this graph? Well, what this graph means is, look at, it's starting way up here, and then it's swooping down. So consider if she only bought one flower. I said it's a deal. It's not a deal. To buy one flower, she's going to have to pay the 32 bucks and the $1.50. And so for one flower, it's very expensive. The way to make this a deal is to buy more and more flowers, because the more flowers you buy, that $32 starts getting split up among more and more of them. But if you're only getting one, the whole $32 is going to that one flower. So the idea is that if you buy more and more flowers, you get a better deal. And it's all about what it's approaching. So when it says, what is the meaning of it? A horizontal asymptote is always what your value is approaching. And so my average cost is approaching, my Y value is approaching that $1.50. So what is the actual meaning? As Carly buys more and more flowers, and here's where it is. The average cost per flower, and here's the key part too, approaches, because that's what's happening on an asymptote, approaches $1.50. That's the real meaning of what's happening here. Now, let's try an example. What would the average cost if she did 12 flowers? Well, now you're just doing your function and you're saying, all right, what is the average cost if X is 12? And we just plug it in. I'll just go to the regular version. I don't have to have the factored out version, and just type that into my calculator and see what we get. I end up at $4.17 per flower. That's the average cost. Now, that remember, that's $4.17 per flower, right? That's not like her total cost. It's the average cost per flower. All right, so I have a couple more of those very similar setups. Give that a shot, and hopefully you can wrap up this whole rational packet and be done when you come back to school. Thanks.